following video is the Zoom presentation of a MassDEP UMass Drinking Water Small Systems intern project on climate and land use changes by Prasad and Megan Anderson. The MassDEP UMass Small Systems intern program is funded by a U.S. EPA Safe Drinking Water Act grant to MassDEP in support of small drinking water systems throughout Massachusetts. This collaboration began when MassDEP's Yvette DePisa, Michael Maynard, and Art Skrapidis saw opportunities for drinking water community involvement and operator training with students of UMass under the leadership of Professor David Reckhow, Professor John Tobiasen, and research engineer Patrick Whitbold. Previous intern projects have worked on lead in schools, small system assistance, operator certification, and other current drinking water topics such as PFAS. MassDEP would like to thank all of their partners on these projects, including the U.S. EPA, MassRWA, FERCog, RCAP, and the UMass Group, especially Professor Reckhow, Patrick Whitbold, and the student interns. They have done hard work on this and all their other drinking water projects.
I'm Megan.
And I'm Ani.
And we're going to be talking to you today about the impacts of climate and land use changes on specifically small systems. So, a little bit of background on climate change. I'm pretty sure almost everyone in this meeting obviously believes in climate change, but just some facts for you and how it specifically relates to water systems and how it affects them is that Massachusetts has seen a steady increase of annual rainfall and temperature rises for the past few decades, and they've also seen an increase in the magnitude and frequency in two-day storms, which has increased about 71% since 1971. So the whole reason why this is important relating to small systems is because more rain leads to more runoff and flooding, which then leads to more pollution that contaminates our watershed and nearby water bodies, which needs to be accounted for when water is being treated either in a wastewater setting or even in a drinking water setting. Now, a little bit about watersheds. So Massachusetts is separated into 28 major watersheds, and they're defined based on the land and the environment around there affecting certain water bodies in that area. So water treatment facilities within these watersheds need to account for the specific chemical makeup that is in their watersheds and nearby water bodies in order to effectively treat them.
And any kind of increase in precipitation can impact the watersheds. It can increase turbidity levels, it can increase the organic matter that you find, or like Megan said, increase the chemical makeup itself, because sometimes in rural areas, if you have more runoffs, that means off farmlands, you can get more pesticides into natural bodies of water, which is something that I think water operators need to keep in mind. And also we're seeing, we talked about in the first slide, a general trend in the increase of precipitation, annual precipitation over the past few decades. And because we're having an increase in the temperature, we're also seeing a gradual increase in rainfall and a decrease in snowfall, which means that in snowy seasons, we see less snowpack and more rainfall.
Yes, and the less snowfall in these seasons and the less snowpack is just affecting the water quality overall, meaning that more water is being run off rather than being left in the snowpack. Therefore, small systems need to account for the increase in flow rates into their system due to this runoff.
Yeah, an example of that is the South Deerfield system, which is really close to us here at UMass. I think they were established in 1971, so about 50 years ago, and they were originally built to deal with about 0.5 MGD of flow, and that's a million gallons per day for people who don't know what MGD means. And they've made some adjustments to their system, but they've never really adjusted the infiltration system to deal with higher flow rates, and I think that's really important to look at, and that's something that people should be thinking about.
Mm-hmm. So I am from Dartmouth, Massachusetts, in the southeastern part of the state, and so I asked the head civil engineer of the town of Dartmouth there, who I used to work with. I asked him about his concerns relating to Dartmouth's wastewater treatment system specifically, and what his main concerns were regarding climate change and land use changes and such. And one really interesting point that he brought up is that the original pipeline for the inlet into the wastewater treatment system or pipelines and such under the ground were originally above the water table, but because of this increase in rainfall, higher precipitation that we're seeing over the years, the water table is now above the original pipeline, leading to higher levels of infiltration, and that water that's being run off and brought into the water table also contains a lot more hazardous pollutants than it did way back when, which is another main concern and is necessary to recognize when wanting to treat that water that's being brought into the system. Okay, so kind of gearing away from climate change, all of these are really connected, but we're going to talk a little bit about land use changes. So urban versus natural environments, which are rural and farmland areas, have very, very different concerns when it comes to pathogens and indicators that enter their water systems there. So from the urban environment, most of the water is brought into rivers and nearby water bodies through runoff rather than direct infiltration into the soil because it's obviously covered in more concrete and stuff like that. But when you get into the farmland and rural side, you can see that there's less runoff, but there's a lot more infiltration, and more pesticide use in natural environments can lead to more infiltration of these toxic chemicals into the watershed and affecting nearby water bodies as well. Okay. So like I mentioned in the last slide, there are two different kind of pollutants and indicators that we're worried about that are affecting the water systems in these specific watersheds. So in urban environments, you are more susceptible to seeing higher levels of bacteria and viruses. And then you can also see a lot higher levels of heavy metals like copper, zinc, cadmium, lead, and a few others. But these usually come from roofs and car-related sources. And on farmland and rural sides of things, you can see an increase in harmful pesticides and nitrogen and phosphorus pollutants. And between the both of them, there is a common level of salts, which has been proven to inhibit the performance of anaerobic digesters.
And about that point of anaerobic digesters, just because we work in a lab that does testing on wastewater treatment systems, we just decided to look a little bit into it. And we found out that anaerobic digesters are actually really environmentally impactful and harmful because the final step in the digestion process is to produce methane. But there are some researchers at universities like Cornell and Texas A&M who have actually found a way to inhibit the methane process and produce carboxylates, which are way more useful because they're like chemical precursors to useful products such as gasoline and jet fuel. So it was just like a thing that just kind of looked into.
Mm-hmm. So next we're going to discuss the importance of low impact development practices. So kind of like what Ani said, trying to find more sustainable solutions in all of these processes and mitigating these pollutants in our water is extremely important. So all of these systems that need to be implemented to treat the water should be sustainable and cost effective, especially for for small systems. So one of the main ways to remove heavy metals from urban pollutants is a bioretention method. And there was a study done that showed a certain media mix of different sands and loams and all that stuff could decrease the amount of these harmful heavy metals in the outflow of the system. So if you can see, that little red box is showing the mean percent removal of each of those specific heavy metals in each of those columns. So the top left section is for reactor 1, which is made up of sand. Top right is zeolite, and then sandy loam and quartz. So these percentages are extremely high, so these systems have been proven super, super successful in the long run, and they're sustainable and fairly cheap, so they should be implemented everywhere. Another way to implement a low impact development practice is another very similar method using a biosand filter. This is proven to get rid of bacteria and viruses in water. So depending on the plant and the filter media makeup as well, and whether or not there is a submersion zone, which you can see in the top image. There's not really a level of water in the middle of the soil, but then when you get to the bottom image, you can see that there's a higher level, which is the submersion zone that they refer to in the study. And it shows on the right how different design decisions can kind of, I guess, change the output of your outflow. And overall, it has been seen that there's a higher removal of FIB, which is like E. coli and stuff like that, from using specific vegetation. And this is a graph of the bacteria and virus in general, or mainly I think it's E. coli in this graph, decrease in the outflow of the system. So another practice is green infrastructure. So both of those methods I just discussed can honestly be implemented as green infrastructure or even in the water treatment facilities themselves. Activated sludge is the most common type or most common method of treating water, but if these chemicals can be mitigated, like what me and Ani were saying about watersheds in the beginning, if we can just mitigate those right off the bat, we don't have to worry as much about implementing certain stages within the water system treatments themselves. So on the left is an example of an infiltration trench out in Yarmouth, Massachusetts. Then on the right is a wetland in, I think that's the UNH campus. Okay, so lastly, a way to get rid of pesticides in the water is, the main point is to educate the public, because pesticide usage is extremely important depending on where you live. So I had no idea that I lived so close to a zone 2, and a zone 2 is an area in Massachusetts that, or zone 2 or an interim wellhead protection area, is a zone in Massachusetts or an area in Massachusetts that is super susceptible to impacting primary recharge areas. So they are extremely important in controlling the water quality of the watersheds and nearby water bodies. And there's a list of pesticides and so many regulations to make sure that you're complying with the groundwater protection compliance in the state. And I had no idea that was a thing. I didn't know I lived a half a mile down the road from a zone 2. So I think educating the public, although fairly difficult, it's a difficult process at times, is extremely important in the case of pesticides. Another way to remove pesticides is through aquatic plants. So it's been found in Echornetia crassipes, I think, is the scientific name of this plant. It's been found to decrease the amount of phosphorus up to 55 to 81%, depending on if it's a shoot or a root. So it's been proven that the roots of these plants have a higher effectiveness in removing these phosphorus-based pesticides from the water.
Mm-hmm. And also because we're in rural areas, there's a lot of use of herbicides, like Megan said, pesticides. And the really common one that's used, I think, is called clomazone. The actual, I think, product's name, I think, is either Command or Commence. I'm not really sure, I don't remember it, but clomazone is a really common agricultural herbicide. And we found that, like, a bunch of studies found out that using macrophytes, which are aquatic plants, again, you can actually remove this clomazone from the water. And it was found that water lettuce, which is a really common one, found in like swamps and other ponds around Massachusetts, actually has a 99% removal rate of clomazone. And the best part about that is that it doesn't accumulate any of the clomazone in its own tissues and doesn't damage itself, which means that we can keep reusing the same specimens or species of water lettuce to remove these herbicides from the water. And lastly, the last low impact development we want to talk about is electrochemical treatment. We're interns at Clarity, so we decided to do a shameless plug for Clarity. So some of the processes that are conducted in drinking water treatment are coagulation, flotation, and disinfection. And these three are the ones I'm picking out because these three processes can actually be done by a single electrochemical reactor. So the electrocoagulation and flotation processes can be done by the reactors like the one that Clarity has, And for people who don't know, like coagulation is basically when you have solid particles and you try to like collect them and make them float to the top and convert them to flocks, I think they're called, and then you can remove those solid particles pretty easily. And the disinfection process, which involves, I guess, the addition of chemicals like chlorine and fluorine, can be done inside the reactor itself, because reactors like this one can actually produce the chlorine gas that's required to disinfect the water.
So that's it.
Thank you guys, and thanks for throwing that last slide in there, that marked it in for our clarity. Just going to say, everyone take that with a grain of salt. There's some merit to the technology they said, but there is a lot to digest beyond that one slide. So we have time for one question, if anyone wants to step in. Someone other than Bob.
Yeah.
Anyone else? Otherwise, okay, 3, 2, Bob, it's all yours. Go ahead.
Okay, I have one ask. We've seen an increase of TOC in a number of reservoirs, Central Mass, Connecticut, and we're wondering if that seems to be maybe something that could be related to climate change also. In other words, not just phosphorus and nitrogen, carbon coming into the system, and the carbon makes it difficult for water plants to effectively remove that carbon, especially if they're only rated about a 50% reduction. If your carbon goes from 2 to 4, now all of a sudden 50% reduction isn't that big, or still a problem. In other words, there's still quite a bit of carbon left that will form THMs. So that's one of the things where I don't know if it's related to you know, this whole issue of climate change, but with more rainfall, more erosion, that means more carbon, I would think. So it might be something you want to look at.
We didn't actually look into that, I don't think, but I think I might have glanced through a bunch of studies that did say something similar to that. So yes, that's expected.
Thank you guys, everyone. Thank you very much.
You guys are doing a good job too.